Welcome to this presentation. This is a report on exploring multi-spectral remote sensing, satellites, capabilities, and environmental applications. My name is Supong Udwagosu George, PhD student in environmental engineering, Mapua University, Philippines. This presentation is made today, the 13th day of June 2025, and is in partial fulfillment for the course titled Application of Environmental Remote Sensing in Environments. The objective of this presentation is to clearly explain the principles of multispectral remote sensing, emphasizing Earth observation satellite capabilities, and demonstrating how multispectral data supports environmental monitoring and decision making. The outline of this presentation is shown there on the screen. It's supposed to be a 5 minutes presentation, so a lot of things will be skipped, which you can read on the screen. Introduction to multispectral remote sensing. Here I'll be giving definitions and key characteristics. Multispectral remote sensing is a technique that captures imagery across multiple specific spectral bands. And this is bands of the electromagnetic spectrum. Unlike panchromatic imaging, which records data in a single broadband, multispectral sensors collect information in distinct wavelengths, such as visible, near infrared, and shortwave infrared. This allows the enhanced material differentiation and environmental analysis. The advantages of panchromatic imaging over hyperspectral imaging is listed over there. Enhance spectral information, improve environmental monitoring, and that's for the panchromatic imaging. And for the hyperspectral imaging, a number of bands, multiple spectral sensors typically captures, 3 to 10 bands, whereas hyperspectral sensors record hundreds of narrow or bands. Its application scope, multispectral uh, imaging is widely used for land cover classification, vegetation health assessment, and water quality monitoring, while the hyperspectral imaging is most suitable for mineral exploration and detailed chemical analysis. Let's compare other remote sensing types, differences from panchromatic and hyperspectral imaging. The differences between these three panchromatic, multispectral, and hyperspectral sensors, you can see that the panchromatic sensors capture imageries in a single broad spectral band, typically covering the entire visible spectrum, or the multispectral sensors capture imagery in multiple discrete spectral bands, such as visible, near infrared, shortwave, infrared, and so on. The hyperspectral sensors capture imagery in hundreds of narrow spectral bands. Or in all of these, there is need to strike a balance. When there's balanced spectral coverage in multispectral imaging, when this balance is attained, the spectral detail and the practical usability normalizes. It provides enough spectral bands to differentiate environmental features while maintaining manageable data volumes and efficient processing. Balancing also makes it highly effective for tracking vegetation health, detecting water pollution, and monitoring land use changes. Earth's observation satellites with multiple spectral sensors. I'm going to do an overview of at least 2 satellites and their capabilities. I'm looking at Landsat 9 and 8 and Sentinel-2. Landsat 8 and 9 are part of NASA's Landsat program, providing multiple spectral imagery for environmental monitoring. I've discussed it in spectral resolution, spatial resolution, and environmental application. It's basically used for land cover classification, vegetation health assessment, water resource management, and climatic changes studies. Or the Sentinel-2, on the other part, is operated by European Space Agency, the ESA, consists of Sentinel-2A and 2B, providing high-resolution optical imagery. They also operate in spectral, and their spectral resolution, they're highly equipped with multi-spectral instruments, and they offer 10-meter resolution for visible and near-infrared bands, etc., for spatial resolution. In terms of environmental application, it supports agriculture, forestry, water quality monitoring, disaster response, and urban planning. Both satellites provide critical multispectral data, enabling scientists and policymakers to track environmental changes, assess ecosystem health, and support sustainable resource management. Let's talk about the spectral and spatial resolution more in multispectral imaging. By this, I'm just going to narrow down to how resolution affects quality. In multispectral imaging, spectral resolution and spatial resolution both significantly impact data quality, both in different ways. In the spectral resolution, um, this refers to the ability to distinguish between different wavelengths of light. Higher spectral resolution means the sensor can detect specific wavelengths, which improve the ability to identify material detected and detected changes. And our spatial resolution determines the level of detail a sensor can capture in an image. Higher spatial resolution means a finer details, allowing for sharper image that makes it easier to analyze small structures. Lower spatial, resolution can result in blurry or pixelated images, reducing the ability to distinguish individual features. There's always a balance between these, which I talked about before. And balancing this resolution is very crucial because it improves uh, uh, because improving one often comes at the expense of the other due to technical limitations. So a high spectral resolution typically requires larger pixels, which can reduce spatial resolution, while a higher spatial resolution might limit the number of spectral bands available. So the ideal balance would depend on the application. If precise materials identification is the priority, like in mineral mapping or environmental monitoring, high spectral resolution is favored. If capturing fine details is more crucial, such as in urban planning or forestry analysis, high spatial resolution will be uh, will be taken into consideration. Application of uh, environmental application of multispectral remote sensing. We're looking at the application of multispectral remote sensing in the areas of vegetation health monitoring, water quality monitoring. It is used in urban sprawling and land cover classification. It also used in disaster management, emergency preparedness, and disaster assessment, to be very specific. The use of a NDVI, a normalized difference vegetation index, is widely used remote sensing tool, and this helps to assess vegetation health by analyzing how plant reflects near infrared and red lights. Healthy vegetation reflects more NIR lights and absorb red lights, while stressed or sparse vegetation reflects less NIR and more red light. So key applications using the NDVI in the environment, you see it in the areas of deforestation tracking, drought analysis, crop health assessment. And If you're looking at how multispectral sensors detect algae blooms, sediment levels, and pollution, is also applied in there. So you see algae bloom detection, sediment level monitoring, pollution detection, monitoring of coast waters and freshwater ecosystems. It is also applied in tracking deforestation, urban expansion analysis, and sustainable urban planning. Multispectral remote sensing provides valuable insights for policymakers, conservationists, and urban planners, ensuring that data-driven decisions for sustainable development are being taken as and when due. Now, let's talk about sensor characteristics and environmental monitoring. Understanding spatial, spectral, and temporal resolution in remote sensing. Spatial resolution has impact more on image detail. Spectral resolution has to do with enhancing material classification accuracy, and temporal resolution has to do with tracking environmental changes over time. You can find these details as I've put them together here on this screen. Together, these resolutions determine the effectiveness of remote sensing in environmental monitoring, challenges and limitations. There are issues with long-term environmental assessment using multispectral data. One of that is as atmospheric interference. The second one is storage and processing challenges due to large data volumes. I want to also point out trade-off between spectral detail and spatial coverage, just to put them in perspective. Please find out details as I've put them there, because I've mentioned in terms of atmospheric interference, the cloud cover blocks satellite sensors from capturing surface details, leading to missing or distorted images, haze and aerosols, mitigation strategies, and so on. In terms of storage and processing challenges, high resolution imagery, large files, demand cloud-based storage resolutions and high performance capturing for analysis. And in trade-off between spectral detail and spatial coverage, you find out that high spectral resolution provide detailed materials classification, but often result in lower spatial resolution. Capture other details as written on the screen because of time. In summary and takeaways, I want to say that multispectral remote sensing is a powerful tool for monitoring Earth's ecosystem, capturing data across multiple spectral bands to analyze vegetation health, water quality, land use changes, and climate patterns. It enables environmental assessments, supporting conservation efforts, and sustainable resource management. Policy implications: climate adaptation, in land conservation, and sustainable urban development. So in climate adaptation, multispectral data help track temperature shifts, glacier melting, and extreme weather events, guiding climate resilience strategies. Land conservation, government use satellite imageries to monitor deforestation, habitat loss, and biodiversity changes, informing conservation policies. Sustainable urban development in remote sensing supports urban planning, green space preservation, and pollution control, ensuring that eco system is friendly and the city and has an eco-friendly city growth. Call to action. Researchers, policymakers, and environmentalists can leverage upon spectral data to develop evidence-based policy and climate adaptation and land conservation. Enhance disaster response by monitoring environmental hazards in real time. This can be done in real time. They can also promote sustainable agriculture through precision farming, different techniques of precision farming. We can use this, so they can also harness multiple spectral remote sensing, ensuring data-driven decision making, fostering a more resilient and sustainable future. Thank you for listening.